Awesome. Well, thank you guys for doing this. Yeah, I think there's definitely a lot of need for, better as far as even with workflows in our world, right? Like when we're dealing with automations, there's a lot of best practices that we want to make sure like we're doing, especially when we're using, a vector database like Quadrant Vector Database, which again, I'm a huge fan of because of the fact that it has the open source capability. But just in general, like I said, especially when we're dealing with large data sets, that's where we want to make sure that we, have a discussion and understand what's the best practice when it comes to kind of cleaning up that data before inserting it into a vector database for better search, for better retrieval process, and all of that good stuff. So maybe I think that, like, as a first kind of topic of discussion, that would be kind of a good segue into getting into the details of how do we handle like large scale data to make sure that the performance is better.
Jump in here.
Hey David, your video is like very blurry, so I don't know if that's on my end or your end.
I
Tim, do you see his video blurry or am I just seeing that?
Yeah, a bit blurry indeed.
Okay.
a bit blurry. Would you mind if I turn off the camera?
Uh,
Or
sure.
maybe
Go ahead. All right.
okay. So there are a few topics when it comes to working with large data. Let's say you're working with like a large amount of data for like a CRM with like millions of customer records, for example. Because we're trying to talk about something applicable to the user. First of all, the core technology of Quadrant is the HNS proximate nearest neighbors algorithm and the index that's built using this algorithm. So there are a few core challenges, which are ingestion speed, query latency, and how to scale the database as the data grows, right? Because you're adding more and more user data. And so Quadrant tackles these challenges with its HNSW based index, which is really designed for approximate nearest neighbor searches. And the indexing approach is great because it gives you a good balance between accuracy and speed. And you can just keep adding millions of vectors and still get quick responses. But there's another aspect to this index, which is the query optimization, which you always need to be very mindful of as you're building up the index, and you have to practice a lot of performance tuning just to make sure you're getting things right. So it comes down to managing a few parameters that we want to let everybody know that are important to maintaining this index, like the EF search range, and we have this in our documentation. I think we can link to it later. The EF construction, which affects how the HNSW graph is built and queried. So there are these two EF and EF construction parameters that help maintain the index. And higher E might give you like a better recall, so you're more likely to find all the relevant neighbors. But it also may mean slower queries. So you're always having to trade off things as you're building up this index. It's also striking about the right balance for your use case. So it all depends on what you're doing. If you need super low latency, you might reduce one parameter, and if you need top-notch accuracy, you might bump it up. But I don't think that's just it. I think there's also different aspects other than the index, which is the sharding and the replication of the database. So beyond the index itself, you have to consider the architecture around it. And Quadrant supports sharding, so you can split your data across multiple nodes or instances. And this way, you're not really overwhelming a single server if your data is massive.
Mm-hmm.
I don't know, Tim, maybe you want to throw in some additional info regarding this, because I know you're an expert in this topic and replication as well.
Yeah, I wanted to mention two key things. First of all, Quadrant is basically distributed by default. So you mentioned shards, and you can have multiple replicas of shards. And this makes it very easy to move data around and scale your cluster up or down, either horizontally or vertically. And actually, we have very recently, I believe a week ago, released a feature in our cloud where we can actually reshard data, so change the number of shards on the fly. And the other key thing I wanted to mention here is that we allow to change a lot of these parameters at runtime. So if you're looking at your current setup, you can basically tune it on the fly and make things happen without downtime.
Awesome. Yeah, no, that sounds. And excuse me, as far as kind of, I know you guys talked about kind of the performance side of things. Like, is there a way to optimize like the query performance? Because obviously when it comes to scalability, right? Like when you're adding, especially when it comes to CRM data, as your data set grows, and then obviously there's when we're building workflows as a backend, especially with N8N for large data sets that are handling all of these updated records that keep coming in, right? So obviously there's the option to upsert, a data inside a vector database. So I'm just curious as far as like the best practices there to make sure like, scalability is optimal. Like what are the best practices from that perspective?
You want to tackle this one so I have to talk the whole time, Tim?
I'll go first. You mentioned how can we improve performance, basically, right?
Yeah.
There are a few key things. First of all, if you talk about quadrants, you can enter points, and points may have payload attached. And if you want to do filtering on these payloads, the recommendation here is to create a payload index. So this allows quadrants to basically build an optimal index of some payload and its value. So if you query by it, it will try to retrieve your data in the most efficient way possible. Another thing I want to mention is quantization. So we support quantization, and basically the idea is that we reduce the resolution of your data a bit to make it smaller, and in some cases a lot smaller, without having too big of an impact on accuracy. So in some cases this can reduce your data by like 32 times, which is huge, of course. And it doesn't just mean you can put more data on your node, but it also means you search through it faster. Another thing is memory mapping. In Quadrant, we call this on disk. For a lot of features we have, for example, the payload indexes, but also the vector data, we allow you to set a on disk true flag. And this will basically put all your data on disk, and your data will be used from disk directly. So one of the major problems before was vector data is very big, so it tends to use a lot of memory, and machines go out of memory very quickly. And the solution of putting data on disk prevents this problem and allows a lot better scaling. And we're actually changing the defaults a bit to use this approach by default for everything. David, anything you want to add here?
Yeah, I'd like to talk about a real company that we work with that wanted to optimize their queries. And they have a lot of data. It's a sentiment analysis company that has a lot of vectorized comments and things like on TikTok and social media, but then they also have a huge amount of metadata to maybe describe the influencer in different ways, or maybe the user details. So we're dealing with a company that has around 5 terabytes of supposable information. And what we're trying to do is search over all this information, both the vectors and the filtering of the metadata, the payloads. This is quite a bit of stuff that has to go in the memory. So the way we reduce it is, as you said, Tim, in a few ways. We have to quantize it. Quantizing means compressing. So you were compressing this text. It loses a little bit of accuracy, but it's not a big deal. It's more of a big deal when you're compressing images. When you're compressing text, you can still retain the same meaning. Yes, it is by around 32 times. If you're using binary quantization, the scalar is around 4 times the drop in memory. So this 5 terabytes can become like 300, 400 gigabytes worth of data stored in memory, which is a pretty dramatic drop. And then we also have the payload, which can sometimes, if not relevant, be offloaded to the disk and not kept in memory. So most fields should be kept, most metadata fields should be kept on the disk because you're not accessing all of them. And the ones that matter, such as, is this TikTok influencer compliant with PG-13 or whatever, that kind of a field would be kept in memory for quick retrieval to check whether somebody's advertising their products properly and whatnot. So we're filtering, we're quantizing, and we're only really exposing these quantized vectors in memory, and everything else is going on the disk. So only the stuff that we need is available for quick retrieval, and then everything else is offload it. And then the thing that you can do in case you suspect that there is a lower search quality, you can start rescoring your vectors, right? So the things that you come back with in terms of results, you can line them up and rescore them against the original vectors, which is a much smaller number, and they're sitting on the disk. And then you can rearrange the importance of the things that have been retrieved just to double check. And this is kind of a second, third step in our retrieval that really makes sure that whatever the result is correct. So there are tricks you can do. And I think this is the biggest strength of Quadrant is you can optimize, you can stretch things to the max, but then once you do, there are best practices and little things you can pull to come back with very, very high quality results.
Okay.
And maybe a key thing to mention again is you can change all these parameters on the fly, right, in your existing collection, because it can be very hard to get the full picture right from the start, especially if you're starting small.
Yeah. No, that's very interesting actually. I is this unique to you guys as far as just this much you mentioned that's quite significant when you're reducing the size of the data that much. Is that or is this kind of like a common practice, or is this just particular to Quadrant?
So there are companies out there that have binary quantization, not to the same implementation. However, what I think is probably the biggest draw, and after this you can correct me, Tim, is our efficiency in filter through the search. A lot of companies out there, as you build up this index and you quantize it and everything, you quantize the data, you have to, take things away to have a more optimal search. You have to filter things through. So what most companies do, they either pre-filter or they post-filter. The significant thing with Quadrant and why it got so popular in the first place is we filter simultaneously. And we call this the filterable vector index. So the HNSW index has been built in a certain way. It's a custom implementation where the links of the graph are severed throughout filtering simultaneously, but it still builds additional links to traverse. The search process builds additional links to traverse to get to its intended result. I don't know if I'm explaining this 100% correctly, Tim. Please jump in.
No, you're doing a good job. I mean, what I can say about this is, imagine you have this huge graph and you have a very strict filter, and you basically filter out 95% of the points. Basically, when we search through this graph, we have a random entry point, and we try to walk through this graph and find the best matching vector, right? But if we have this very strict filter, we disable a lot of these points and links we have in there, and that the result of this might be that we might not be able to reach the best possible point in the graph. So what we do to make this a lot better is we generate this graph like others do normally first, but then we enrich this graph with extra links between a lot of points that are aware of the different payload values there are. So this makes sure that if you filter to some specific payload value, you'll always have some links across all the graph, basically to find the point you're looking for.
Yeah.
And Quadrant has been very proud of its benchmark results over the last 2 years. Now these are of course always changing. We recognize that everybody out there is inventing new features and new ways of doing things, but generally we have a very, very high accuracy in retrieval, and this is probably one of the biggest draws to the customer, right? Anyways, I think that's we have a few topics to cover.
Yeah. Yeah, no, that makes sense. No, that's good. Thank you. Yeah, I'm sure we would take a look at this further down some, because that's definitely, I think, a huge feature and a very useful feature. And imagine especially when it comes to dealing with larger data sets, whether that's CRM or other data as well. So that's a huge opportunity there for sure. Yeah, that's great. So, and then kind of maybe it's a good segue to understanding how the, I guess the integration or effective strategies for integrating vector database like Quadrant into our AI workflows or automations or chatbots. document search, because that's what we do, right? A lot of times we use a vector database like Quadrant for RAGs, and we want to make sure like we're doing, we're having the effective strategies to integrate this vector database for better search and better retrieval when it comes specifically to RAGs inside NNN, of course, because that's what we build a lot of workflows with. So I just wanted to see if we can talk a little bit about that and what are the best practices there in order to make sure that we're building, agentic wraps the proper way and retrieving the documents, or whether it's done via chat or some external application that reaches to the vector database to retrieve the information that's needed. Like voice bots are now becoming extremely popular. So that's a very good use case where you have this knowledge base that's sitting inside vector database. And then in the AI workflows, you can essentially have the voice bot reach out and retrieve the information that's needed from the AI agent.
Yeah. So when it comes to integrating a vector database like Quadrant into various AI workflows, let's say for this voice bot or a chatbot or anything like that, a document search tool, or it could be a recommendation system, anything like that. We actually built, let me just do a little bit of a segue, we built Quadrant initially to be a search engine, and then around May 2023, I think RAG became a big deal, and we all went with it. But the general idea is the same, right? You generate embeddings, so you create vectors from data, whether it's voice or text or image. You store them. These are high-dimensional numbers, vectors, and then you query them. So you have calculations be done inside of Quadrant that retrieves the result. So typically, when you're integrating, you'll have a pipeline where you take your raw data, like a text document, a user profile, or something like a product detail, and then you run it through an embedding model, maybe like some type of a fine-tuned transformer model, some embedding for images or voice, and then depending on whether you need domain-specific understanding, of course, you need to pick the right model. So then this model will create embeddings, store it with any relevant metadata like user IDs, timestamps, or categories, and you'll store that in a Quadrant collection. So if you're building a chatbot that needs to retrieve images or answers in real time, you would embed the query on your side as well, right? So you're trying to match your query against the data inside of the database. You send that query embedding over to Quadrant, which finds the closest, calculates the closest and the most relevant embeddings amongst your stored data. And then you can either display those results directly, or in terms of RAG, you can pass them to another model for re-ranking or answer generation. I think this is where people like to hear about Quadrant the most, right? Is creating the context for our LLMs to use. Let's talk about something that happened the other day. Let's talk about DeepSeek, right? The big deal is DeepSeek is controversial at times because it may not give the most correct answers, depending on people's opinions, I guess you could say. When you have context sitting behind a model like this, you have specific information stored inside of Quadrant. This information can be then retrieved and fed back into DeepSeek or another generated model, and then you get the answer that you need, right? The thing that's also interesting is this filtering that I want to get back to. Once you have all your vectors in Quadrant, you can still filter by metadata fields like we talked about. So if you want your chatbot to only show documents from a particular department or to a particular user, you can even chop your collection up by user types, usernames, user departments, or locations, or anything like that. So it's very easy to run Quadrant as a single database and have personalized data be served to various iterations of chatbots or different builds. In terms of architecture, we're really optimized for that. And in terms of microservices from a practical standpoint, I think integration is pretty straightforward. And Tim, you can jump in after this, but we have a REST and we have a gRPC API, so you can wrap everything in a microservice, and your AI system will just kind of ping that microservice that gets results back. Right? So you're building a chatbot, and this is what you'll be doing. There's really no complicated internal logic required. And this really is powerful because then you can scale each part of your system independently, which is, of course, appropriate for large production environments.
Yeah, you're exactly right. I don't have much to add here, to be honest. If you want to improve your rack stuff, basically a lot of it depends on the quality of your models, and you can reduce the scope of your rack by using our payload filters.
That makes sense. Yep, absolutely. All right, so I'll give you guys, because I know I think one of the best features, at least from my perspective for Quadrant, is I think that the data visualization feature that you guys have. I mean, that's amazing to kind of see, that it maps almost kind of like, I mean, it's not in 3D, but just the fact to see that you can actually hover over, the different data points and, the fact that, the data gets vectorized and you can actually see how close the different clusters are. I think that's a very cool feature. So I don't know if you guys have like an example of that somewhere sitting already that you could show, but if not, obviously I know you guys mentioned that you have a few more things that you wanted to talk about and show a few things. So yeah, would love to kind of open it up for discussion. Then afterwards, we'll just take some questions from the folks on the call.
Yeah, so I think what we should drop in the comments from this chat afterwards is the link to our WebUI tutorials. We have a dashboard, essentially, the same way that Elasticsearch has Pybana. Of course, Elasticsearch was originally made for structured data and logs and things like that. And our dashboard is interesting to people because it shows unstructured data and the way it's stored and distributed inside of the database. The visualization feature, and I wish I had it with me right now. I definitely would have been excited to show you, but it basically, the coolest thing about it is it tells you if your embedding model is working properly, right? If it's grouping the data properly, it means it's properly tuned to understand what it is that you're feeding it. This is a big deal for machine learning people who are trying to understand the appropriateness of their entire pipeline and trying to evaluate the situation. I think the thing that people need to realize with the vector database, our biggest problem is not necessarily that we don't work properly. Our product works great. But in order to work with the database, you have to feed stuff in it. So your ingestion pipeline has to be correctly set up to get that retrieval right in the first place. So it's important to us to teach people about the way they're chunking their data, the way they're embedding their data, the way they're prioritizing different pieces of information to index and filter out. The dashboard that we have helps people do those things. And it's very rudimentary. We've had an extremely capable intern who joined our team afterwards, designed this JavaScript application or a React, application. But yeah, that's it for the dashboard. I do maybe want to give Tim a chance because Tim is the guy who knows everything about the roadmap and he knows all the secrets. So maybe Tim, you can tell us about some stuff coming out this year because we just came up with a roadmap, I think, today.
Nice.
Today.
Yeah, so actually in the meanwhile, I have set up a Quadrant instance and loaded some sample data. So maybe I can make it work to show this visualizer.
And you can use so we can load it with regular data sets. You can put in the Midjourney one because people like seeing that one.
Yep.
So we can show people how like images and stuff is connected. It's very cool to check out. Everybody can do this for free, by the way. If you go to quadrant.tech and you sign up for the free cloud instance, you get, I think, a gig or something like that, and it's plenty of memory to try stuff out. And you have the data ready, so we make it all available for you.
So shall I just share my screen and give it a shot?
Absolutely, yep.
Is it visible yet?
Yep.
Yep.
Awesome. So what I just did in our Quadrant cloud interface, I created a free cluster, so you can do this at home as well. Don't steal my API key, please. Now, once you have started your cluster, you get to this interface, and here are also the tutorials David just talked about. So if I click on here, I see quite a few. It's a lot of fun to go through these. Also, here we have a datasets button, and here I just imported the Midjourney styles dataset. And what it's given me is this collection. I called it podcast just now. And here we see the data in our collection. So what we have is we have these images. And now if I go to the, first of all, let's see, I guess this one may be a bit more interesting. David, do you happen to know some ideal parameters for this?
Yeah, so do a limit 5, sample 900 or 1000. And then tree true. So you would build a tree. There you go. So you run that. So this one's a lot cooler, and you can stretch it out. Right? You take a little node and you pull it out to unravel this clump of stuff. It's yeah. So I think you gotta pull it harder. But the idea is that once Tim unravels this big mess of unstructured data, right? This is unstructured data, so it is all kind of related to each other to a certain extent. But what we're trying to find out is what's closer to each other, which pieces of information, which pictures are relevant, and when we do the search, which nodes will come up as results. So let's scroll to, just zoom in to something that has more points close to each other. So let's see that thing. What kind of pictures do we get? Those are women wearing dresses, right? So if you're looking up a picture of maybe a historical picture of a woman wearing a dress looking through a window, you would be served all of these alternatives as a potential result, right? This is how a vector database operates. It serves you alternatives. The semantic functionality will find very, very closely relevant things. And the relevancy is determined by the embedding model. So this image, this graph right here, is a good gauge of how well your embedding model is arranging the data. If it's all over the place, if it doesn't make sense, then basically that tells you should pick a different model, or you should chunk your data differently, or you should do something else in the ingestion pipeline in order to get your stuff correct.
Oh, so you're saying that you can, when you're vectorizing your data, you can come obviously to this particular visualize section and actually see if they're not accurate as far as, because obviously you can hover over or click on those little dots and it'll show you exactly what the different pictures are. And if you see any kind of inaccuracy, so that's when you're saying that you probably have to rechunk and use another embedding model, correct?
Exactly.
Okay.
Right. And that's what we're doing right now. We are actually experimenting with models on our end, which are at times not correctly tuned. And whenever we want to see that it's working, we'll embed some data, and then we'll go look at this graph. And if it's right, then it's tuned properly. And if it's not connected, then we have to redo the tuning again.
Yeah, this is very cool. Like I said, it's just, I mean, it's one thing to kind of understand what's going on in the background, and that's why, like I said, this is probably like my favorite feature, because like it's really, it's to visualize this and actually see, and the fact that you can like expand this. And by the way, what is this expansion like? So when you're expanding the data there, Tim, or like when you're grabbing the different tree nodes, like is that just for us to just kind of easily see what's going on, or does that actually do anything to the actual data inside the database?
No, it's just the visualization we show here. Like it gives this clump of branches, right? And I just take out a branch here, so it's a little easier to see.
Yeah, that makes sense. Okay.
And just to clarify once more, like these in one single branch are all very similar visually. So in this case, you could say it works very well. If I go to some other branch, like the one we saw just now, this is clearly very different. While these points that are close are very similar.
Oh, okay. So basically, the closer these data points are, that means that those images in this particular case are the ones that are like closely related, or like, that woman in the dress and stuff. Okay, that makes sense. Okay.
So this,
And by-
this visualization feature, sorry, Tim, please go.
Yeah, I just wanted to mention, currently it's a bit bare bones, and we really want to extend this feature to make it maybe even more general purpose and to give you a lot more tools to explore your data. That will be fun.
Oh yeah. I think honestly, like this would be something that would be a very, um, unique feature that I haven't seen it in any other. I mean, I've played Pinecone and Weaviate and other vector databases. I haven't seen anything like this. So that's why I was like, this is a very cool feature.
So this is built on top of our distance matrix API, which calculates the pairwise distances between points. So this JavaScript application or this React application is just calling the distance matrix API that I think released in version 1.12, maybe 1 or 2 versions ago, something like that. And we're just going to continue building on top of this. This specific example you're seeing is fairly cool. I actually had a ridiculous experience when I was writing the article for this. So this is called the distance matrix API. And then I opened up this graph of these same mid-journey pictures. I hovered over the first image. And the first image that I hovered over was Neo from the Matrix. So can you imagine that?
That is freaky.
Yeah, so I think I had a sample of 900. So whatever the probability score is for 1 out of 900 is, yeah, it was pretty random. So I knew this was meant to be.
Yeah, that makes sense. No, this is very, very cool for sure. So what are you guys planning to add to this? Tim, you mentioned you're planning to expand this or add more features to this.
To be honest, I'm not quite sure yet.
Okay.
We have to dive into what works, right? So.
Okay. Yeah, that makes sense. Of course, yeah. I mean, it's one thing to...
I was thinking of adding clustering, but I think there's a bit of manual work that has to be involved in getting the results of clustering right. There are these algorithms that you can implement, but not all of them are going to be showing data correctly. I was talking to Andre, the CTO, of doing the embeddings projector. It's kind of similar to that TensorFlow embeddings projector. We'll see. It'll probably be a few versions before something comes out. We're testing things for the users.
Yeah, that makes sense. Cool. Yeah, so let's, I know Tim, you mentioned you wanted to talk about something else for a couple of minutes, and then, yeah, we'll just maybe because I know Dale's on the call and Gavin, others, like maybe if they have any questions, we can have them jump in.
Sure. Yeah, we mentioned how about new features. So first of all, we did a release about 1 week ago. Another significant feature we implemented is GPU indexing. We didn't mention this yet, but the key thing here is that you can use GPUs to build your indexes, and this can be about 10 times faster, while having a machine that is similarly priced. So that's actually a fantastic achievement, and huge if you want to build clusters with a huge scale. So this should allow you to go to 1 billion vectors easily. And also things we're working on now, one of them is incremental HNSW. So the idea is that we use existing HNSW graphs and expand them a bit as data changes. This will allow you to build these indexes even faster. Another thing we're working on is read-write segregation. So right now, you basically just have one quadrant cluster by default, but the idea is that we, in the future, allow you to have separate clusters, many for reading and one for writing to scale even further. And maybe another fun thing to mention is we're internally building a serverless-ish approach. So the idea is here that you just create a collection, you give us your parameters, and we scale this thing for you, and you don't have to bother about tuning your collection and stuff like this.
Nice. Yeah.
If people want to try out the thing that's available right now, so we just came up with GPU acceleration. We have it available not just for NVIDIA, right? This is a big deal. We have it for AMD. We have it for other vendors like Intel. Because we're not using the CUDA approach. We have Vulkan API that we're sitting behind on this implementation. So this is fairly compatible across the board. And some of the GPUs, the higher powered ones, can achieve up to 10x. But I think this is more of a budget play. So For the same amount of money that you would pay for the comparative amount of CPUs, you can get a much faster, I think moderately around 5 to 7 times speed. I think what we're trying to do is not tell people to use like the big GPUs for LLMs here. We want people to try mid-range GPUs because Quadrant is a product that was generally only made for CPUs in the beginning, right, for the search. So right now we've developed a system to index using the GPUs, but it does not have to be the most high-powered ones. If people want to try indexing large amounts of data, my recommendation is to pull the specific images from the Docker registry now. So we have an AMD or an NVIDIA image available as of last week or something like that. And we have documentation on the site that is just a few more configuration steps to set up the instance. And we like people to try it out and come back to us. It's important to have this indexing feature for highly dynamic use cases, right? Let's say we're ingesting data from forums or Reddit or something like that, where new stuff is coming out all the time. You have to continually replenish this index, and the speed comes really into play in those kinds of use cases. If you're only indexing once, then maybe not so much. But if you're indexing all the time, then you should look into paying way less with the GPU.
And one fun thing I have to mention here is I'm not sure if you're aware of what a Steam Deck is, but it's basically this portable gaming handheld. And in December we had this retreat with the company, and some of us brought this Steam Deck. And this nerds thought like, hey, let's create a cluster of Quadrant on Steam Decks and use this new GPU feature on the Steam Deck and index your data fast. And actually worked like right out of the box. So it was fantastic.
Nice, very nice, cool. All right. Thanks, guys. All right, so let's go ahead and open it up for questions. Dale, I know you've been waiting patiently, so go ahead, jump in.
To be honest, I don't have questions. I'm just getting started with this, and it's to be honest, for me, let me move my mic close. It's like drinking from a fire hose and trying to learn a brand new product. So I'm just trying to, be overwhelmed with this particular piece of the automation platforms that I'm doing.
So the question I have is, mine's more of like a pricing sort of thing. Obviously, I've tested Superbase on time zone stuff, and I don't particularly like either one of those for various reasons. So that's why I'm interested in this. But I was just wondering, pricing wise, where does it sort of stack up? You know what I mean?
Yeah, so David might be the better one to answer this, but compared to the competitors we have, we tend to be a bit cheaper. And also this new serverless feature we're working on should be a lot cheaper, especially for smaller data sets. I hope that's a satisfying enough answer, but let me know if it isn't.
I think it's true, but the thing that you have to consider is we offer extensive optimization features that Superbase does not. Superbase, good product. I think it's overall very strong, but we're specialized for the things that we do. So you definitely have to think through whether the optimizations that we offer work for your use case. If so, then you can have very, very significant savings, even on top of the regular price. So as we talked about in the call today, compressing data, right? Filtering through data, offloading data to disk. All those features are not available on many of the other products, and having those will dramatically reduce the cost. Just the data compression itself makes it so you have to pay way less in memory and compute.
And also, Quadrant is open source, right? So you can run it yourself, and we also have a hybrid cloud, so you can provide your own hardware, and we run Quadrant on it for you, and you basically pay for your own hardware.
Yeah, so you're not paying for a hosted service if you don't want to.
Yeah, because essentially, I mean, if you're, because it's open source, I would imagine if you're, running it on your own machines, if you have pretty powerful machines, I would imagine, then as far as the cost of the vectorizing, I would imagine it's nothing, right?
Probably not. I mean, if you're vectorizing video or images, if they're very rich, you have to be careful about the embedding model that you pick.
Right.
If you're just talking text, that's nothing.
Mhm.
That's like not even worth, unless you're doing like billions of vectors. But anything like 100,000 million vectors or something like 1,000 documents, it's not even worth talking about.
Yeah, that makes sense. Okay, cool. Well, thank you guys for doing this. I appreciate it. This was definitely a lot to take in. Of course, like we'll you know, especially I think the most important conversation I think that we had was just around like kind of best practice for large database design when it comes to like vectorization, especially when it comes to using vector database in the AI workflow. So that's a huge asset. Yeah, Dale, go ahead. You had a question?
Can I ask a stupid user question or a newbie question on this? I'm currently self-hosting this, and if I were to like deploy it up in the cloud, what's the best practice for having multiple clients? Should I have one instance per client, or should I put it like one client gets their own collection? Because it doesn't. That thing that was really confusing me on the self when I'm playing with this.
Go and look up multi-tenancy on our site. We have documentation dedicated to this, and we also have a dedicated article teaching people how to do everything. So the general rule of thumb is you always use the same collection for multiple users. This affects performance, affects cost. You just have to chop up the collection according to the tenants. So a tenant can be defined in the metadata, and there is additional configuration parameters. But you should check out the docs itself. It's right under multi-tenancy. If you're not doing anything crazy different, and you're just doing like, a RAG application for multiple users, then the go-to answer is always one collection, multiple tenants. And then the next thing you just have to think about is how you shard it. If you're in need of some type of a distribution later down the road, then you should consider the distributed deployment documents we have as well.
Basically, the recommendation is to only use different collections if your data doesn't match up. So you have, for example, different kind of vectors or different vector sizes or something like this. And by the way, I linked the documentation that we just talked about in the chat here.
Yeah, I saw. Thank you. I'll take a look at it.
I do want to mention that we have a very, very active Discord channel. This is not for customers. This is for everybody, right? Anybody who's a hobbyist, anybody who's experimenting, anybody running the free version. You're doing whatever you're doing in the basement, trying stuff out. We're there for you. So me and my team are support people. So Quadrant does have a Discord. It's very busy, very active, and our CTO is very gung-ho. He's answering everybody's questions. So if you want to talk to the CTO and the guy who made up Quadrants, your best bet is to go to Discord and start asking some random questions.
That sounds fun. Yeah, I might have to join that. All right. Cool. Well, if you guys don't have anything else, any last thoughts, then yeah, again, thank you guys so much for doing this. Definitely very informative, and hopefully we can do kind of more of these moving forward, because like I said, there's definitely a huge use case, especially when it comes to building workflows with vector databases. And like I said, especially I'm a huge proponent of open source platforms, so I definitely appreciate companies that have that mentality as well. So, but yeah, thank you guys again so much for doing this, and hopefully we'll sync up again soon.
Thank you, Zubair.
All right. Thanks, guys.
For having us.
Yep. Have a good one, Tim, David. Take care.
Bye.